Now, this one's a little bit different. You need to make good note of this. Students who overlook this one little fact will get these problems wrong. Okay? Take a look at your dividend, the polynomial that's being divided. You notice it starts with an x to the fourth term, but skips right to an x squared term. You notice that, right? That's a problem. That will cause you to get incorrect answers when you perform the long division. Make a note of this. There's a missing x to the third term. When you set up your long division algorithm, every single term has to be represented. If you start with an x to the fourth term, then every other term of smaller degree has to be represented underneath the long division bar. And here's how you do it. You start with 8x to the fourth. Now we add an x to the third term that has no value. How do you add something that has no value? 0x to the third. You must have that there, otherwise the long division algorithm won't work. It has to be 0x to the third as well. If you put it 1x to the third, then that's a term that has value, so you're adding something to the polynomial that shouldn't be there. 0x to the third has no value. It's just a placeholder is what it's called. Okay? The divisor goes on the outside. And same thing with that. If the divisor is missing a term, it has to be represented with the placeholder of a 0. And the process is the same as the last one we did. You start by considering just the first term here and just the first term here. How many times does 2x squared go in to 8x to the fourth? 4x squared. Yep. So 4x squared now multiplies through this whole entire divisor. 4x squared times 2x squared is 8x to the fourth. And it's important that this first term matches the term just above it, because when we subtract, those first terms have to cancel. 4x squared times negative x is negative 4x to the third. 4x squared times 2 is 8x squared. Now what happens? What do you remember from last time? Draw the line underneath and subtract. Okay, now there's a couple of ways that you could do this, whichever way you want to do. If you're careful and can think without really writing, you could just put a parenthesis around it like this and make sure you subtract every term. Some students do really well with that, others don't because they get careless. The other way that you could do this, rather than putting parentheses around the entire thing, this is what actually most students do. It's a goofy little phrase, but it seems to work. You draw the line and change all the signs. Draw the line, change the signs. That'll at least help you remember that you're subtracting every term. First terms cancel. 0x to the third plus 4x, that's a 4x to the third. 6x squared minus 8x squared is negative 2x squared. And then you drop down this term and begin the process. Again, this is also something students forget, but how do you know when to stop? How do we know that this is not the remainder? It's not necessarily because there's another term to drop down. It has to do with the relationship between this first term and this first term. Since this still has greater power, then we still have to keep going. Once this has one smaller degree than the divisor, then you stop. Okay, so once we get this down to a linear term, then we stop. So anyway, 2x squared into 4x to the third power is 2x, yep. And if you're struggling with coming up with what term to put on top here, what you could do is just take the first term of your divisor and the first term down here and divide them. If you take 4x to the third and divide 2x squared, that's going to leave you with 2x. So that's the term that will come up here. Anyway, multiply the 2x, 4x to the third, minus 2x squared, plus 4x. Draw the line, change the signs. Both of the first terms cancel. That doesn't happen very often. We get a negative 7x, drop down the positive 1. And this is the remainder. We know that because this negative 7x plus 1 has a degree of 1. The divisor has a degree of 2. Since this has a smaller degree, we consider that the remainder. Okay? So the result of the division, if p of x was divided by, what did we call it last time? Q of x? I can't even remember.
Wait, I got a question.
D of x? What's your question?
So it says negative 4x cubed plus 2x squared plus negative 4x.
Where's that?
Just that last step in the one.
Let's see, right here?
Yes.
Okay.
So you got negative 4x. If you're subtracting negative 4x, wouldn't you be adding 4x? So wouldn't it be x? Negative 3x plus 4x would equal x.
Well, 2x times that 2 right there made a positive 4x, but when you draw, you have to subtract.
Oh.
So you have to change the sign. So it's a negative 3x minus a 4x.
Sorry.
That's okay. So when the original polynomial p of x was divided by d of x, the divisor, the result is right here. 4x squared plus 2x. That's the quotient. Then you add the remainder, negative 7x plus 1, and you divide that by the divisor. This is how you represent your solution. 4x squared plus 2x plus negative 7x plus 1 all over 2x squared minus x plus 2. Your homework will be asking you to represent this an alternate way as well. This is probably the more common way. But they will ask you to also do this. If you take your quotient, which is 4x squared plus 2x, if you multiply that with your divisor, and then you add the remainder, this is the quotient, this is the divisor, we add the remainder. What should that equal if all this were simplified and expanded? Yep, you're right. That should equal the dividend, what we started with. 8x to the 4th plus 6x squared minus 3x plus 1. Now let me just explain why we're learning this and the direction we're supposed to be heading. The next two sections after this, 3.4, we're going to skip 3.5, we're going to go right to 3.6. Those two sections deal with finding factors of polynomials that divide it evenly. How do we know if something divides a polynomial evenly? How do we know if a number divides another number evenly? If the remainder is, if something divides a number completely, there's no remainder, right? That's what you've learned since elementary. 2 divides 8 evenly because it's 4 with remainder of 0. So what we're getting to eventually is we need to find factors of polynomials to divide evenly. So there will be no remainder. The remainder is going to be 0. Let's move on to what's called synthetic division. You're going to like this one more. It is faster. So given some division problem to do, p of x divided by d of x, and this is important. your divisor, d of x, the denominator, has to be of the form x minus c or x plus c. So if it's a linear expression that has a leading coefficient of 1, you can synthetically divide the two polynomials. It's much faster than long division, usually more accurate. Problem is, it only works in this case. Okay, you can only do synthetic division when your denominator looks like something x minus c or x plus c, where c is just a number. Okay, so let's go back to the two examples that we just looked at. Example 1. Could we have used synthetic division on this? If we look at the denominator, that's of the correct form, x minus 4. So we're going to actually redo this problem here in a second using synthetic division. What about example 2?
No.
You cannot use synthetic division here because your denominator is quadratic. Okay? The denominator has to be linear. So let's take a look. Let's do example 3. Let's actually redo problem number 1. It was 6x squared minus 26x plus 12 and that was divided by x minus 4. Bless it. Okay, synthetic division starts with an upside down long division bar like that. Okay. Inside you're going to put the coefficients of your dividend, but make sure you leave space at the bottom. Take a look at what I'm doing here. Just the coefficients of the dividend, I'm going to have a 6, a negative 26, and a 12, but there's space beneath them to write other numbers. Synthetic division only deals with coefficients, no variables, just numbers, coefficients. The number that goes in front of the upside down fraction bar is what's called the critical value of the denominator. Okay, and you might remember this back from our first unit. What would turn the denominator into 0?
4.
That's called the critical value. So you put the critical value in front. Okay, this is a different process than long division. It gives the same result, but it's different. So you have to run through this a couple of times before you really get it down. And we are going to, in section 3.4 and 3.6, we're going to do synthetic division probably 40 or 50 times. So you're going to get a lot of practice with synthetic division. Here's the algorithm or the process. The first term always drops down to the very bottom right here. Always drop that first term down. Numbers beneath here always multiply with this critical value. So 6 times 4 results in 24, and you write that result right here. Numbers that form the column inside of the upside down bar always add. Negative 26 plus 24 is negative 2. And since this number is on the outside, what happens to it? You times it with the 4, write the result right here. Since these form a column, we're going to add these. 12 plus negative 8 is 4. Here's how you interpret the results. The last number is the remainder. Now flip back to example 1. Check example 1. Did we get a remainder of 4? Okay? These numbers here, these are the coefficients of the quotient. Coefficients of the quotient. Quotient means the result of the division. And if you start from the right and go to the left, the furthest number to the right is a constant. And if you move one to the left, that will be a linear term. So this is a coefficient of a linear term. That's just a constant. So the quotient is 6x minus 2. Then we add the remainder, 4, over the divisor, which was x minus 4, and that's the result of the division. 6x minus 2 plus 4 over x minus 4. Check and compare that to example 1. Exactly the same, right? Synthetic division. It's faster. Well, it only works in certain cases. You have to know long division because long division works more often. Yeah.
So even if it was like 2x minus a number and one.
Oh, if it can. It's much more difficult, and we're not going to get into that, but it has the potential to. Hey, what's up?
I got a question.
Yeah.
Does your word work?
Yeah, is yours not?
No.
I had the guy who came out to mine a few days ago. Let's try another one. Part B. Two x to the third minus 7x squared plus 5 is going to be divided by x minus 3. Yeah. I'm glad somebody noticed. Make a note of this. Missing. What kind of a term are we missing? We're missing an x term. So that also does have to be represented using synthetic division. So when you do the algorithm, the coefficients of the dividend go inside, but we have to place a 0 where the x would be. So this is a 2, a negative 7, and then a 0, and then a positive 5. The critical value of the denominator is going to be 3, so that's what we're synthetically dividing by. Drop down this first number to the bottom and then start multiplying. And then numbers that are lined up in columns add. Empty. An empty spot where? Oh, nothing ever goes there. You always just drop down that first term. Okay, so this is your remainder. These are the coefficients of your quotient. Now some students wonder, well, which coefficient goes in front of which type of a term? Everybody look up here. Stop what you're writing. Put everything down. Pay attention to the screen. If you have a third-degree polynomial that's being divided by a one-degree polynomial, what's the result going to be? A second-degree polynomial. So these are the coefficients of a second-degree polynomial. This is going to be a 2x squared term. This is a minus x term. And that's just a minus 3 constant. Okay? Let me repeat that. We have an x to the third term being divided by an x to the 1 term. So the result, or the quotient, has to be x squared. So the result of this division is 2x squared minus x minus 3 plus negative 4. Yep. Over x minus 3. Okay. Now, let's represent this a different way. So draw an arrow from here. Your homework is going to ask you to do this as well. If you take the divisor and multiply it by the quotient, so the quotient was 2x squared minus x minus 3. If you multiply that with the divisor, x minus 3, and then subtract the remainder. So this is the quotient, this is the divisor, and we added the remainder. What should the result of this all be?
2x minus 7x squared plus 5.
It's a different way of representing what we just did. I'm going to keep mentioning this so you get the connection. The direction that we're heading is to find remainders of 0. We want to have remainders of 0 eventually. Here it's not that important. In this section, it's not that important we get a remainder of 0. But just watch, don't write. I want you to watch. If x squared plus 7x plus 10 is divided by x plus 2, watch what happens synthetically. We're going to have a 1, a 7, and a 10, and negative 2 goes out here, drop down the first term, perform the synthetic division, and the remainder is a 0. Okay, in the next section, this is important. Okay, it's important that we get a remainder of 0. Why? Instead of representing the solution this way, okay, what if we represented the solution this way? If the remainder is not there, then x squared plus 7x plus 10 is equal to the quotient, which is x plus 5, times the divisor, which was x plus 2. And what did we just do there? Factor it. Now, I know you could probably argue, well, it's easier to factor the other way. And yes, that's true because this is pretty easy to factor. But what if I give you a 4th degree polynomial to factor that has 5 terms? Okay, do we know techniques to factor that? No, but if we perform synthetic division and get remainders of 0, we'll eventually be able to write that 4th degree polynomial in factored form. You see where we're going with this? That's why we need to get remainders of 0. That helps us factor. Okay? Let's keep going.
What about that triangle thing?
Triangle?
Like, I don't know, whose triangle is it?
Oh, Pascal's triangle?
Pascal, yeah.
That's for expanding. Something like x plus 4 to the 5th. That would be an example. Well, if we have time, we'll get to that at the end of the semester. Remainder Theorem. If P of x is divided by x minus c, then the remainder has exactly the same value as P of C. Just to read through a definition from a math book sometimes is pretty confusing. Okay? The more you read them, the more you get used to mathematical language. What this is saying is, if I took some random polynomial and divided it by something of the form x minus c, okay, synthetically. Now, if we did the synthetic division, we'd have the coefficients of P of x here, right? We'd get some remainder here at the end. Hold on to your question 1 second. Can you guys visualize this? And here we would have the value c. The remainder that we would get from the synthetic division is the exact same value that we would get if we performed the evaluation P of c. These two would have the same value. Okay? Now I know that might not have explained anything further, so let's try an example. Here's the polynomial. 3x to the 5th plus 5x to the 4th minus 4x to the third plus 7x plus 3. If I asked you to find p of 2 by hand, no calculators, remember, that's going to equal 3 times 2 to the 5th plus 5 times 2 to the 4th minus 4 times 2 cubed plus 7 times 2 . You just plug it in, right? You plug it in for all the x's. Is this going to be necessarily easy to do by hand? Not so much. We can do it, but it's not going to be easy. 2 to the third power, or I'm sorry, 2 to the fifth power is 32. And then 32 times 3 is 96. 2 to the fourth power is 16. 16 times 5. Let's see, 16 times 5 is 80. 2 to the third power is 8 times negative 4 is negative 32. 7 times 2 is 14, and then we add 3. Woo! Now 96 plus 80 is 176. Then we subtract 32. Then we add 17. 176 minus 32. 144. Then we add 17. Ooh. And that's going to equal 161. So yeah, it can be done by hand. It's not pretty, nor is it very much fun. Let's try this using the remainder theorem. Okay? The remainder theorem says, do this synthetically. Take the original polynomial, p of x, put the coefficients here. Where did this 0 come from? We're missing an x squared term, so you have to have a 0 in there. The one big difference here the students mess up on is in this form of synthetic division, you use the exact number that you're trying to evaluate. You don't change the sign. So we are going to synthetically divide using a positive 2, not a negative 2. Now if you perform the algorithm here, let's see, 158, I think. What is being shown here? What's the value of this remainder theorem? Or what's the point of learning this remainder theorem? Take a look at the remainder. It's the same value that you get by just doing the plain evaluating. Okay? And that will always work. The remainder theorem says the remainder of synthetic division is exactly the same as evaluating the original polynomial at that point. So you got to decide what was easier for you or more enjoyable. You can just do the plain evaluating here, which does take some time. The number's a little large. Or you can do the synthetic division, which usually goes faster. There are pros and cons. I mean, you could make mistakes with evaluating. You could also make mistakes with synthetic division. So it's up to you. Let's try part B. Do you have a question? Are we on example 4? Part B. Try one on your own. polynomial is 6x to the 5th plus 10x cubed plus x plus 1 find p of negative 2. I'm trying to do this using the synthetic or the remainder theorem method and not just plugging it in and trying to evaluate it out. Did you notice there were 2 missing terms? So you had to have 2 placeholders in there. And we're synthetically dividing by negative 2. We do not change the sign when we're doing the remainder theorem. So drop down 6. It's negative 273. You would get the same result had you taken a negative 2 and plugged it in for all the x's. Okay, last part of this is what's called the Factor Theorem. This is hinting at what I spoke about a few minutes ago, that the whole point of learning synthetic division or long division is eventually to learn how to factor polynomials that can't otherwise be factored using techniques that we already know about, like grouping or factoring out common factors, any of those sorts of things. Okay. Put this in parentheses. This is not included in the definition in your book, but let's put it in there. To be a factor, x minus c must divide with no remainder. To be considered a factor of a polynomial, it has to divide it with no remainder. This will be the last example just to illustrate this factor theorem. Example 5. Which one is it? 4, 5, 10? Example 4.5. We'll go right in the middle. P of x equals x to the 3rd minus 7x plus 6 show that x minus 1 is a factor of p of x, and then find all the zeros. This last phrase, find all the zeros, is going to be the phrase you're going to see in every single problem in section 3.4 and 3.6. That's the whole point of both of those sections, is to find the zeros. If you're forgetting what zeros are, what are zeros? I told you a bunch of synonyms for zeros. X-intercepts or solutions. Okay? That's really what we're getting at in 3.4 and 3.6, is finding solutions to equations by finding zeros. The way that we've found zeros in the past is by factoring, but does anybody know a technique for factoring x to the third plus or minus 7x plus 6? It does not factor using the techniques we know of at this point. Okay. What's that? So we do have to do synthetic division. They're asking us to show that x minus 1 is a factor. So we got to perform the synthetic division. We have to put a 1 and then a 0 placeholder because the x squared term is gone. Then a minus 7 and a plus 6. Now we're doing synthetic division like we learned it originally. If we're dividing by x minus 1, we have to use the critical value of x minus 1, which is 1. So we're synthetically dividing by a positive 1. Right. What is it we're searching for, by the way? How do we know that something's a factor? What should we get? No remainder. That's what we're going for here, no remainder. So if we do the synthetic division, we get a remainder of 0. What you then do is take p of x, x to the third, minus 7x plus 6, and you write it like we were writing a few minutes ago. You take your quotient, this is your quotient right here, x squared plus x minus 6. You multiply that with your divisor, which was x minus 1. And usually, wouldn't you add the remainder at that point? But there is no remainder. And because the remainder is 0, look what we have done. We've partially factored the original polynomial into x minus 1 times x squared plus x minus 6. What proves that this is a factor? How have we proved it?
Well, if you multiply the both sides together, you don't get that.
True, and we've shown that there's a remainder of 0. Okay, now take a look at this, the quotient, x squared plus x minus 6. That can be factored further into x plus 3 times x minus 2 times x minus 1. So by using synthetic division, we fully factored a polynomial that otherwise we didn't know how to factor using a traditional factoring techniques. This is fully factored because there's 3 factors. It was a third-degree polynomial to begin with. Now we're ready to answer the final question. Find all of the zeros. The zeros are from the factors. X equals negative 3. X equals positive 2. And x equals 1.
3, 2, 1.
Correct. Okay.